Good morning, students. Myself, Vijay Shankar from ECE department, Chevrolet Engineering College. Today, we are going to discuss about the second topic in the 5th unit, EM Characteristics 2. EM Characteristics 2. So, in this, the reflection of the plane waves, we have so far studied the uniform plane wave. We have so far studied the uniform plane wave, traveling in unbounded and homogeneous medium. But practically, very often, waves propagate in bounded regions consisting several media of different constitute parameters, such as epsilon, mu, sigma, eta, etc. Before we actually start with the reflection of the uniform plane wave, let us consider a simple example of the transmission line. We already completed the transmission line that considered a transmission line having the characteristics impedance Z0, load impedance ZL. If load impedance ZL is equal to the characteristic impedance Z0, then the line is said to be properly terminated. If not, there is a mismatch between two impedances, and the line is not properly terminated. Okay, so consider that the wave traveling along the line incidents at load. The part of wave gets absorbed by the load, while other part is reflected back to the generator. Means whenever there is an incident is there, some part is absorbed, transmitted, and then some part is reflected. Consider the wave traveling along the line incidents at a load. The part of wave gets absorbed by the load, while other part is reflected back to the generator. So we can reflection occurs at the load that if ZL is not equal to Z0. If there are two waves, one incident in forward direction while other is reflected back in the backward direction, then the standing waves are said to be produced along the line. Okay. Now consider again the uniform plane wave traveling in a non-homogeneous medium. When a uniform plane wave travels from one medium to the other medium, having different intrinsic impedances, the reflection takes place at the boundary. The part of wave is transmitted in the medium 2 and remaining part is reflected in the medium 1, depending upon the constitute parameters of the medium. Depending upon the manner in which the uniform plane wave is incident at the boundary, there are two cases. One is a normal incidence, when a uniform plane wave incidence normally to the boundary between the media, then it is known as a normal incidence. It is known as a normal incidence. Got it, my dear students? While other one is an oblique incidence, when a uniform plane wave incidence obliquely to the boundary between the two medium, then it is known as oblique incidence. Then it is known as oblique incidence. Okay. Now, you can see here a normal incidence at a plane dielectric boundary. In this section, with the two dielectric medium, dielectric and conductivity. Okay, consider a uniform plane wave striking the interference between the two dielectrics at a right angle as shown in the figure here. See, in this a medium in between the one is a dielectric, another one is a conductor. Okay, the boundary between the dielectric and the conductivity. Okay. Assume that the uniform plane wave travels in the z direction. Z direction. See here, it represents the z direction, my dear students. Here this is a z direction. E is in the x direction. EX. And H is there in the y direction. So actually it is towards the, which is perpendicular to the EX and the EY, not the EY, it's the HY. And the wave is propagated through to the Z direction. Got it, my dear students? So assume the uniform plane wave traveling along the Z direction and incident at a right angle at the boundary between two dielectric medium at the Z is equal to 0. At Z is equal to 0. Below Z is equal to 0, let the function shows that the properties of the medium 1 be the nothing but it is, let us take it as a parameters only, the epsilon 1, mu 1, sigma 1, eta 1, and above the Z is equal to 0. The properties of the medium 2, epsilon 2, mu 2, sigma 2, eta 2. So, depending upon the properties of two media, a part of wave will be transmitted in medium 2, while other part will be reflected back in the medium 1. Okay, so in this diagram, a part of beam is reflected to the transmitted here, and a part is a reflected wave and a transmitted wave, and there is an incident wave itself. Okay, in the normal incidence only we are discussing here. Let EI and the HI be the field strengths of incident waves striking at the boundary. Let ET and HT be the field strength of the transmitted wave in the medium 2. Once again, see here now, my dear students, this is a boundary line. Let us take this a boundary line. Okay. Now there is an incident wave. Let that is the EI. And also it represented the dot here. HI is also there. HI. And now this is a boundary having the parameters. This is a medium 1, and medium 2. And there is a transmission occurs. At ET. And similarly, some part is reflected here. Let it be the ER. My dear students. And here there is a HT is also there. And here the HR also the term in the normal incidence. So EI and the HI with the field strength of the incident wave striking the boundary. This is a boundary line, my dear students. Boundary line. let ET and HT be the field strength of the transmitted wave in the medium 2, and let ER and HR be the field strength of the reflected wave in the medium 1. So both the incident and the reflected is in the medium 1 now. Medium 1 returning back from the interference or interface between the two mediums. From the figure 12.9.1, let us see here. So there is a incident occurs, EI and the HI. There is a transmitted ET and the HT, and the reflected is there. This is a cross mark and the dot value is means a dot is in the front side, and the cross mark means it is in the back side. The negative direction is a positive direction, my dear students. Incident and the reflected both are in the medium 1 only, and in the medium 2, the transmitted wave, as per the diagram shown there. Okay, from the figure 12.9.1, it is clear that in the medium 1, the total field compresses both the incident and the reflected wave fields. Both are in the medium 1, but in the medium 2, only the transmitted field gives a total field. So the conditions for the total fields in the medium 1 are given by E1 is equal to in the electric field EI plus ER. In the magnetic field EI or plus ER, the combination of the two, because it is in the both are in the medium 1 only. Assume that the E1 bar. Similarly, for the magnetic field, HI bar plus HR bar is equal to ER bar. Not the ER, sorry, H1. Both are H only terms. H1. Okay. Similarly, the conditions for the total fields in the medium 2, E2 is equal to ET bar. E2 is equal to ET bar, or E2 bar is equal to, only we have in the medium 2 the transmitter only, ET bar. Okay. H2 is equal to H2 bar. According to the boundary conditions, the tangential components of E bar and H bar must be continuous at the interface Z is equal to 0. As we know the waves of transverse in the nature, at the boundary we get both the fields E bar and H bar, both the tangential to the interface E1 tan is equal to E2 tan. Okay, according to the boundary conditions, we already know in the Maxwell's equation, boundary surfaces between the dielectric and the conductor, and dielectric and the dielectric. For the continuous E1 tan is equal to E2 tan. The tangential components. So what is the E1 saying? That is a combination of the EI and ER. EI and ER is equal to and the E2, what is the E2? ET bar. The E tangential to the medium 1 and the tangential component in the medium 2, E1 tan is equal to E2 tan, means E1 is equal to EI bar plus ER bar, because both are in the medium 1, and in the right hand side the equation ET bar is in the medium 2. Okay, my dear students. Then so similarly, the H1 tan is equal to H2 tan. Thus, the interface at the Z is equal to 0, we can write as E1 plus ER is equal to ET, and H1 plus HR is equal to HT. These two are in the medium 1 and these two are in the medium 1, and ET and the HT is in the medium 2. Got it, my dear friends? And we know the intrinsic impedance means intrinsic impedance eta is equal to EM plus by HM plus. Okay, HM plus. So the combination, the relation between the magnitudes of E bar and H bar at Z is equal to 0. Given the following sequences, EI is equal to eta 1. Eta 1 is in the medium 1 minus 2. So eta 1 is equal to, from this equation, we can write as eta 1 is equal to E I by the HI. EI by the HI. And the eta 1 is in the same medium, but whenever you can write as a reflection, for incidence it is a positive value, the reflection is a negative direction. So ER by HR. Okay. And similarly in the transmitter, that is in the medium 2. Medium 2 means one of the parameters is there, eta 2 is in the medium. So eta 2 is equal to ET by HT. ET by the HT. Now you can write the EI is equal to from n eta 1 into HI plus ER is equal to minus eta 1 into HR, and ET is equal to eta 2 into HT. Eta 2 into HT. Now we have the equation is that EI plus ER is equal to ET. EI plus ER is equal to ET. What is the EI here? Eta 1 HI plus, and ER is a minus eta 1 HR is equal to ET is nothing but eta 2 into HT. Okay, check the eta 1 is a common term. HI by HI minus HR is equal to eta 2 into HT. Eta 2 into HT. Okay, HI minus HR is equal to eta 2 by the eta 1 into HT. Got it, my dear students? We got these equations to find the coefficients, reflection coefficient and the transmission coefficient. Okay, reflection coefficient and the transmission coefficient. EI plus ER is equal to ET, and the HI plus HR is equal to HT. Then you can represent that function as EI by the eta 1 minus ER by the eta 1 is equal to ET by the eta 2. So EI minus ER is equal to eta 1 by eta 2 into ET. So in terms of HI minus HR is equal to eta 2 by the eta 1. This is in terms of the electric field. In terms of the magnetic field, HI minus HR is equal to, here it is eta 1 by eta 2 becomes here eta 2 by the eta 1 into ET. Got it? So adding the two functions, what is the two functions here? EI plus ER and EI plus ER is equal to ET. Add the two functions, we'll get cancel of ER. 2EI is equal to 1 plus, here the ET is there, here also the ET, 1 plus eta 1 by eta 2 into ET. So 2EI is equal to, the equation becomes, when we're adding the two functions, the 2EI is equal to eta 1 plus eta 2 by the eta 2, because here they're taking the LCM of eta 2 plus eta 1, nothing but eta 1 plus eta 2, whole multiply the ET. Okay, whole multiply with the ET function. So 2EI, it becomes EI or ET bar is equal to, or ET is equal to 2, cross multiply that, it's a 2 eta 2 by eta 1 plus eta 2 into EI. And the ratio between of ET by the EI, the transmission with respect to the incidence. Without incidence, there is no any transmission and the reflection. So there is a transmission coefficient represented as a gamma. Transmission coefficient gamma is equal to 2 eta 2 by eta 1 plus eta 2. Okay, the transmission coefficient. Transmission coefficient. Got it, madam? Similarly, when you subtract the two functions, whatever the equations we have here, subtract the two functions, EI get cancelled, then we get 2ER is equal to, 2ER is equal to, when subtracting 2ER is equal to, not the subtracting, my dear students, we need it is a EI and the ER only, because the ratio of ER by the EI, the ratio between of ER by EI, that only we can call it as a reflection coefficient. Reflection coefficient gamma. Okay, that reflection coefficient will get from EI minus ER is equal to eta 1 by the eta 2 ET. What is the ET? EI plus ER. So eliminate the ET here. EI plus ER. Now we can simplify. The left hand side and the right hand side, the EI and the ER terms only. Bring the EI here, 1 minus eta 1 by the eta 2. Whole multiply with the EI is equal to, bring the ER in the right hand side. So take the ER as a common. It becomes of plus 1 plus eta 1 by the eta. Okay. Take the LCM both sides. The eta 2 is a term only. The eta 2 minus eta 1 into EI is equal to ER into eta 2 plus eta 1. So you can take the ratio of ER by the reflection coefficient. ER by EI is equal to, ER by EI is equal to, what is the EI coefficient is? Eta 2 minus eta 1 by eta 1 plus eta 2 or eta 2 plus eta 1. This is a gamma. Okay. The reflection coefficient, the ratio between ER by EI, and transmission coefficient ET by the EI. So we got the ET is equal to, or ET is equal to 2 eta 2 by the eta 1 plus eta 2 is the EI. You can write as a transmission coefficient. That is a transmission coefficient denoted as a gamma, or the tau you can see here. The tau, you see, sorry, the tau is representing the transmission coefficient and the gamma is representing the reflection coefficient. So ET by EI is equal to 2 eta 2 by eta 1 plus eta 2. And eliminating the ET, so substitute EIT is equal to EI plus ER and simplify the equation. Simplify the equation here. ER is equal to eta 2 minus eta 1 by the eta 2 plus eta 1. Representing as a reflection coefficient gamma is a gamma here. Gamma is equal to the reflection coefficient is denoted by the gamma, and it is given by gamma is equal to ER by EI. ER by EI, eta 2 minus eta 1 by the eta 2 plus eta 1. Okay. In the normal incidence, in the medium one, there is a two waves, that is the incident wave and the reflected wave. And in the medium two, we have only the transmitted wave. Only we have the transmitted wave. So we got two expressions, eta 1 and the, not the eta 1. Eta 1 is in the medium 1 and the eta 2 is in the medium 2. So EI plus ER is equal to ET. EI plus ER is equal to ET. And relations between of eta 1 is equal to ET EI by the HI, the ratio of the terms, because the incident is in the medium 1. Let us take one of the parameter of intrinsic eta 1 only. And the same eta 1 is equal to minus ER by the HI, and the eta 2 that is in the medium 2, so ET by the HT. Okay, using these functions, you can derive the, substituting the ET, the eta 1 is equal to, or EI is equal to, HI is equal to, or in terms of, okay, you can get the eta 1 and eta 2 values as of transmission coefficient tau is equal to 2 eta 2 by eta 2 plus eta 1 as a transmission coefficient, and the reflection coefficient gamma is equal to eta 2 minus eta 1 by eta 2 minus eta 1 by eta 2 plus eta 1, the reflection coefficient. And this is a normal incidence at a plane of dielectric boundary. Okay, dielectric boundary. There is a transmission is there and the reflection also. Transmission and the reflection. So EI is equal to, from this here we get the one of the equation, that is EI minus ER is equal to, EI minus ER is equal to eta 1 by the eta 2 into ET. Okay, or otherwise simply EI by the eta 1, so HI is equal to, because of the HI plus HR is equal to, when in the magnetic magnetostatics of the magnetic fields HT. So what is a HI is equal to EI by the eta 1, EI by the eta 1, and what is a HR is equal to minus ER by the eta 1, and what is a HT is equal to ET by the eta 1. Okay, so simplify these expressions to get the transmission and the reflection coefficients when the normal incidence, between two dielectrics, normal incidence between the two dielectrics. Now, what is the relations here? From this reflection coefficient and the transmission coefficient, they are saying that 1 plus transmission coefficient is equal to, not the transmission, reflection coefficient is equal to transmission coefficient tau. So let us see that. 1 plus the reflection coefficient eta 2 minus eta 1 by eta 2 plus eta 1, that is equal to, take the LCM of eta 2 plus eta 1 plus eta 2 minus eta 1 by eta 2 plus eta 1. So eta 1 and eta 1 get cancelled. Eta 2 minus eta 1, and here the eta 2 becomes 2 eta 2 whole divided by the eta 2 plus eta 1. So it's nothing but it is a transmission coefficient. So what is the relation? 1 plus the reflection coefficient is equal to tau in normal incidence at a plane of a dielectric boundary. And this reflection coefficient always varies in between of 0 to 1 on 0 to 1. Both the coefficients, reflection and the transmission, have dimensionless and maybe complex in nature. Okay, dimensionless and complex in nature. According to the Poynting theorem, the average power density is given by, see, first of all, remember, my dear students, one of the formula is that the P average is equal to EM square by the eta into 2. You can derive after completion of this a plane of conducting boundary, dielectric boundary of the normal incidence and the oblique incidence. The Poynting theorem, the average power is given by the 1 by 2 EM square by the 2 eta Weber per meter square. Okay. And where EM is the amplitude of the electric field intensity and eta is the intrinsic impedance of a medium. Okay. The average power of the transmitter in the medium 1. So first of all, remember, my dear student, how we'll get this expression means you can derive the later after completion of the normal incidence and oblique incidence between the boundary conditions. P average is equal to 1 by 2 EM square by the eta. So I'm taking the PI average power in the incidence. So incidence means 1 by 2, the E becomes of EI square, and the eta in the medium 1, incidence means in the medium 1, eta 1 only. Similarly, the PR average, this is in the reflection in the medium 1 only, 1 by 2, let it take that PR square by eta 1 only, because it's both are in the medium 1. And coming to the P suffix T average is equal to 1 by 2 ET square, 1 by 2 the ET square, whole divided by the eta, since here it is in the medium 2, eta 2. Okay. Now we can add the terms or take the PI average by the PT average by the PI average, or PR average by the PI average, the ratio between of the incidence and transmission and incidence, and reflection and the incidence. So first of all, if I am taking that is a P suffix T average by PI average is equal to, what is a PT average is equal to 1 by 2 ET by ET square by the eta 2 whole divided by 1 by 2 EI square by the eta 1. So 1 by 2 get cancelled. 1 by 2 get cancelled, and eta 1 will get in the numerator and eta 2 is in the denominator, and ET by the EI, ET by EI ratio between the square term. What is the ET by EI? Already we proved that in the normal incidence of a dielectric medium, ET by EI, the transmission coefficient tau, eta 1 by the eta 2, the transmission coefficient tau square. What is the transmission coefficient tau? Eta 1 by the eta 2 into transmission coefficient is a 2 eta 2 by the eta 2 plus eta 1 whole square. Got it, my dear students? See, in the numerator there is a eta 2, 1 eta 2 get cancelled, and here also 1 eta 2 is get cancelled, and in the numerator the 2 square becomes a 4. 1 eta 2 is get cancelled, another eta 2 is there because it's a square term. Eta 1 and the eta 2 whole divided by eta 2 plus eta 1. What is this? Average of PT by the PI. Okay. Similarly, PR average by PI average is equal to, what is that function? 1 by 2 get cancelled, and again the I is in the numerator, denominator, eta 1 only. R is also the eta 1. So eta 1 and eta 2, eta 1 is also get cancelled, having only the ER square by EI square only. After substituting the formulas of here, PR average 1 by 2 ER square by the eta 1, and PI is also 1 by 2 EI square by the eta 1. So 1 by 2 eta 1 and 1 by 2 eta 1 get cancelled. ER square by the EI. What is the ER by EI? Is nothing but the reflection coefficient gamma whole square. What is that reflection coefficient? Eta 2 minus eta 1 by eta 2 plus eta 1 whole square. Okay, my dear students. Now we got the two functions, PR average and the PI average and the PT average by the PI average. Take adding of the two functions, PI average or the PT average plus PR average whole divided by the PI average is equal to, what is the first function? The PT average, we got 4 eta 1 and the eta 2, and adding the function here, the eta 2 minus eta 1. Eta 2 minus eta 1 whole square whole divided by both the functions having eta 2 by eta 1 whole square on denominator, eta 2 plus eta 1 whole square. Got it, my dear friends? Now you can simplify the function here. Above eta 1 square plus eta 2 square minus 2 eta 1 and eta 2, and plus here 4 eta 1 and eta 2. So 4 minus 2, it becomes 2 eta 1 and eta 2. In the numerator also we got the eta 1 and eta 2 whole square on. So finally we got P T average is equal to average plus PR average is equal to PI average. PI average on. Got it, my dear friends? The combination of the reflection and the transmission of the power, average power, is equal to the incident average power. Got it, my dear friends? You see here, the PT average plus PR average is equal to PI average. Okay. Then you go for the next one is, next topic is a normal incidence at a plane of conducting boundary. Normal incidence at a plane of conducting boundary. Previously, the interface between the dielectric 1 and the dielectric 2. Okay, dielectric 1 and the dielectric 2. But when you go for the a normal incidence at a plane of conducting boundary means in the right hand side the conductivity and the left hand side is a dielectric. Right hand side conductivity is a more means conductivity is a more. Nothing but sigma is a more. If sigma is a more means what is the eta value? The sigma is a more. So what I am saying here, now we are considering a normal incident beam, and here the dielectric is one side, dielectric that is a medium 1, and in the boundaries the next is a medium 2, is a conductor. Okay, all the parameters we have here, the epsilon 1, the eta 1, and the mu 1, and the sigma 1 also. Here, the conductor, epsilon 2, eta 2, mu 2, and the sigma 2, and so on. These are the parameters of them. In these parameters, the conductivity is a more, means sigma is a very much greater than the epsilon value, because it's a conductor. Conductivity is very high. When the conductivity is a very high, the sigma eta is equal to 0. Eta is equal to the 0 value. Why it is means we know the eta is equal to j omega mu by sigma plus j omega epsilon is under root. This is a formula for the eta. Eta is equal to the sigma is very high, means under root of j omega mu by very high is infinite. Infinite plus j omega epsilon. Infinite something, infinite plus something means that is also the infinite only. Okay, 1 by infinite means 0. So eta is equal to 0. But because it is in the medium 2, eta 2 is equal to 0. Eta 2 is equal to 0. This is a very, very important point, my dear students. Since the normal incidence at a plane is conducting boundary, in the right hand side, the medium 2 is a conductor. It having the parameters epsilon 2, eta 2, mu 2, and the sigma 2. Since it is a conductor, conductivity is a more. When the conductivity is a more, the intrinsic impedance is equal to 0. How it is the intrinsic impedance is equal to 0? By using the formula here, eta is equal to. Conductivity is a very high, means infinite. Infinite plus anything is infinite. 1 by infinite is a 0. Eta is equal to 0. Since it is in the medium 2, eta 2 is equal to 0. Eta 2 is equal to 0. Now you got one idea, my dear students. Then, what is the transmission coefficient and the reflection coefficient? Transmission coefficient is 2 eta 2 by the eta 2 plus eta 1. And the reflection coefficient, we got eta 2 minus eta 1 by eta 2 plus eta 1. So now in the conducting boundary, we got eta 2 is equal to 0, since conductivity is infinite, very high. Conductivity is very high, my dear students. Got it? Now you can find out the transmission coefficient when the normal incidence at a plane of conducting boundary. Eta 2 is equal to 0 means transmission coefficient is a 0. And what is the reflection coefficient? Eta 2 is a 0 means minus eta 1 by, and here are the 0 plus eta 1. So both are get cancelled, minus 1. So eta 1 is a minus 1. So when there is an incident beam is there in the between of a dielectric and conductor, there is no any transmission. It is a fully reflected. Whatever the incident is there occurs, some part is reflected and some part is transmitted. But in the medium between dielectric and the conducting boundary, there is no any transmission. Transmission is equal to 0, and the reflection is a minus 1, means whatever the direction we are sending the wave in a positive z direction, the ex, reflection is fully is reflected in the negative direction, the opposite direction. Nothing but the reflection coefficient is equal to minus 1. You see here, transmission coefficient is a 0, and the reflection coefficient is equal to minus 1. From the values of the reflection and transmission coefficient, it is clear that the wave is totally reflected and there is no transmitted wave in the medium. It is obvious from the fact that no field can exist in a perfect conductor. No field can exist in a perfect conductor, no field, either D or E or H or B also. No field can exist in a conductor, perfect conductor. As totally reflected wave combines with incident wave, standing waves are formed. There is no any transmission means total it is reflected, and this reflected wave is combined with the incident wave, then it becomes then we'll get a standing waves. See, there is an incident wave in the medium 2, there is no any transmission, fully it is reflected. Normal incidence at a plane of conducting boundary. A standing waves does not travel, and it consists of two traveling waves, one incident and another reflected. Both the waves have same amplitude, but the directions in which they are propagated are different. Okay, they are propagated at the different. And the reflection coefficient gamma is equal to -1. Using these, the combination of the standing wave is E1S is equal to S means standing wave is a combination of EI plus ER. EI plus ER. EI is a magnitude and ER is also magnitude, and having exponential values e power minus gamma 1 into Z and e power plus gamma 1 into Z. And because it is considering as a E, X direction, AX bar on. Okay, my dear students, we'll discuss.